It is the essence of what we are trying to explain. It's the difference between a machine that can write a perfect sonnet about love and a human who has actually felt it. The dominant scientific theories of consciousness, such as the global neuronal workspace, or GNW theory, focus on the computational architecture of the brain. GNW proposes that you become conscious of a piece of information when it is broadcast across a widespread network of neurons, making it available for various cognitive processes like memory, planning, and language. In this model, consciousness is a functional property of information access. If information is globally available, it is conscious. If it is confined to a local processing module, it remains unconscious. This is a powerful and elegant framework that aligns beautifully with our understanding of the brain as an information processing system. It suggests consciousness is a clever trick of data management. Another leading computational model, integrated information theory, or IIT, takes a slightly different but related approach. IIT posits that consciousness corresponds to a system's capacity to integrate information. It attempts to quantify this with a mathematical value called phi. A system with high phi, like the human brain, has a structure where the whole is vastly more than the sum of its parts. Its components are richly interconnected and interdependent. A system with low phi, like a digital camera's sensor array, has components that act largely independently. For IIT, consciousness integrated information. The higher the integration, the more conscious the system. Both GNW and IIT are hardware agnostic. They care about the pattern of connections, not the stuff being connected. These theories are compelling because they're testable and provide a clear path forward for building artificial intelligence. They imply that if we can replicate the brain's functional architecture, its global workspace, or its integrated information structure, in a silicon-based machine, we will have created genuine consciousness. The machine would not just be an inner life, it would actually have one. This is the orthodox view, the bedrock upon which most of modern neuroscience and AI research is built. It's a clean, elegant, and purely computational story. But what if a fundamental force of nature, one we've overlooked in this domain, refuses to be ignored? What if the stuff matters more than we ever imagined? The radical alternative, championed most famously by the mathematical physicist Sir Roger Penrose, argues that the computational story is missing the most important chapter. Penrose contends that human understanding, particularly our ability to grasp mathematical truths, possesses a quality that cannot be captured by any algorithm. He argues that consciousness must involve a non-computable process, something that lies outside the realm of classical and digital machines. This is not a philosophical preference, but a conclusion he draws from the deep logic of mathematics and computation, particularly Gödel's incompleteness theorems. If consciousness is indeed non-computable, then it cannot emerge from a brain that is merely a complex computer. It must be tapping into something else. This something else, Penrose proposes, is the physics of reality at its most fundamental level. Specifically, he points to the unresolved mystery of quantum mechanics, the measurement problem. In the quantum world, particles can exist in multiple states at once. A superposition. This blurry state of potential persists until a measurement is made, at which point the system collapses into one single definite reality. Mainstream interpretations have struggled to explain what constitutes a measurement. Penrose suggests that it is not an external observer, but gravity itself that resolves this ambiguity.